Before we move further into applications of artificial intelligence, I thought I would spend just a few minutes on one basic question. What is actually happening behind the screen when we use AI? I will deliberately keep this non-technical. We do not need to understand computer science or programming to understand the basic working principle. I will explain it in the same way we might explain a machine, a control system, or an inspection process to another engineer. The simplest way I like to describe AI is as an inference machine. Something goes in, some processing happens, something comes out, and then, importantly, somebody has to decide what to do with that output. The input could be text, an image, an inspection photograph, vibration data, a temperature signal, production data, or even a maintenance history. The AI model examines that information using patterns it has already learned. It then produces an output, perhaps a prediction, a classification, a summary, or a suggestion. For engineers, there should ideally be one more block after the AI output. Engineer check. Does this answer make physical sense? Does it comply with our standards? Is it safe? Does it match what is actually happening on the shop floor? So I would not think of AI as a machine that simply gives us the answer. Think of it as input used to understand inference, which used to get the output, and then engineering verification take place. Now, the natural question is, how did the AI learn those patterns in the first place? A simple analogy is training a junior engineer or a new inspector. Suppose we show a new quality inspector hundreds of acceptable components and hundreds of rejected components. After some time, the person starts recognizing patterns. Whenever I see this surface condition, I should investigate further. Whenever I hear this type of sound from the machine, something may be wrong. AI learning has a similar broad principle, although mathematically it is obviously much more complex. We provide examples, good components, bad components, machine records, documents, inspection reports, images, historical cases. During training, the system adjusts itself so that it becomes better at identifying useful patterns in those examples. Then a new case arrives and the AI applies what it has learned. But there is a very familiar engineering principle here. Garbage in, garbage out. If our examples are incomplete, biased, wrongly labeled, or outdated, the AI can learn the wrong pattern. So good AI begins with good data. Generative AI, such as the systems many of us now use for conversations, works somewhat differently from a conventional database search. Suppose I ask, prepare a maintenance checklist for an industrial compressor. It does not simply go to one stored page and copy the answer. It examines my question and its available context, and then progressively predicts and constructs what should come next in the response. One useful piece leads to another and another until it forms a complete answer. That is why these systems can generate remarkably natural reports, summaries, explanations, and checklists. But here is the danger. The checklist may look excellent. It may have headings. It may have technical terminology. It may look completely professional, but the AI may not know that our particular compressor has a different OEM requirement. It may not know our plant environment. It may miss a safety requirement. It may not know which standard our organization follows. So the output can be an excellent first draft. The engineer still reviews, corrects, and approves it. For industrial engineers, perhaps the easiest analogy is an experienced inspector. Think about somebody who has worked on a product for 20 years. That person sometimes identifies a problem simply by looking at a component or listening to a machine. They may say, something does not sound right. Why? Because 20 years of observations have created an enormous pattern library inside that person's experience. An AI model develops its pattern recognition differently. Instead of human experience, it learns from stored data, photographs, defect labels, maintenance histories, sensor signals, documents, and previous cases. That makes AI extremely useful for saying, please show me where I should look. For example, these 5 components appear unusual. This machine's vibration behavior is different from its historical pattern. These 3 variables seem associated with the defect. That can save an engineer enormous amounts of analysis time. But the engineer's role remains different. The engineer ultimately says, this is what actually happened, this is why it happened, and this is what we should do. That responsibility should remain very clear. This also explains something many people find surprising. Why can such an intelligent looking system sometimes give a completely wrong answer? There are several reasons. First, perhaps we asked an unclear question. The AI then has to infer what we meant. Second, the underlying information may be poor. Third, the information may be old. This is particularly dangerous with standards and regulations because requirements change. Then there is something called an AI hallucination. The system can generate a very fluent and convincing answer even though the factual basis is weak or incorrect. And finally, the AI normally does not have the same physical context that we have. It has not necessarily stood beside your machine. It has not touched the component. It has not spoken to the operator. It has not seen the oil leakage that occurred yesterday. That is why I would suggest one very simple engineering rule. AI output is a draft until verified. Verification can mean checking the original source, calculation, drawing, standard, safety requirement, confidentiality requirement, and, where necessary, physically checking what is happening at site. Fluency should never be confused with correctness. So after understanding how AI works, we can become much clearer about where to use it. There are many relatively safe starting applications: summarizing a long document, preparing the first draft of an SOP, creating training notes, converting meeting discussions into action points, preparing the first version of a checklist. Then there are applications where AI can be very valuable, but we need stronger verification. Compliance mapping, root cause analysis hypotheses, forecasting, supplier comparisons, maintenance analysis, and then there are decisions where I would be extremely cautious about allowing AI to operate independently. Final safety decisions, engineering approvals, legal sign-off, uploading confidential industrial information without proper controls, or allowing autonomous action where the consequences of an error can be serious. So if I had to reduce these 7 slides to one line, it would be: use AI to accelerate. Use engineering judgment to approve. AI can process far more information than we can manually. It can identify patterns extremely quickly. It can dramatically reduce repetitive analytical work. But responsibility for an engineering decision does not disappear merely because an intelligent system assisted us. And with that basic understanding of what is happening behind the scenes, we can now look much more comfortably at where AI can actually help industrial engineering.